In this video, we're going to study how the Laplace transform deals with functions that are discontinuous. Indeed, one of the big motivating factors for using Laplace transforms to solve differential equations is that Laplace transforms are going to deal with discontinuous functions very well. So in this video, we're going to start our investigation of how the Laplace transform is going to deal with discontinuous functions in general. And perhaps the best spot to start is the simplest of the discontinuous functions, perhaps. It's just the step function. This step function, which we write u of t minus a, basically is just 0 on one side when t is less than a, and then is 1 on the other side when t is greater than or equal to a. So it just basically just looks like this. It looks like a step. Now, we've actually already studied the Laplace transform of the step function, so I'll just put up the answer here. Effectively, what happened is that an integral from 0 to infinity got truncated to an integral from a to infinity by the step function, and then you can compute all that in proper interval. You got e to the minus sa divided by s. Okay, so that's fine. But I'm now going to turn to a slightly more general case, which is a step function times some other function f, also at t minus a. Also evaluated at t minus a. The idea here is that I want to think of this as just being the function f, but it gets turned on, if you will, at the point t equal to a, and that to the left of t equal to a, it's just going to be 0. That's the effect of the step function. If I try to write it as a piecewise function, basically it's just going to be 0 to the left, and then it's going to do, well, whatever the function does to the right of t equal to a. I really like this because it allows me to take a lot of piecewise defined functions that have jump discontinuities and just write them as a product of a step function, which we're going to understand very well, and then just some other function. So then the question is, well, how do I take the Laplace transform of things of this nature? So let me just begin with the definition of the Laplace transform. Once again, the capital F of s is defined to be, well, the integral from 0 up to infinity of e to the minus s. I'll use tau now. F of tau d tau. Tau is just a dummy variable. We often use t here, but I'm going to do a change of variables, so I'm leaving it by a different dummy variable named tau in this case. Anyways, that's the definition of the Laplace transform. Now, and I'm slightly working in reverse, knowing where this is going to go, now I'm going to try multiplying both sides by e to the minus as. On the left side, that just, well, I just multiplied by e to the minus as, nothing happened. But on the right side, notice where the multiplying by e to the minus as ended up. It ended up inside of the integral here. And the reason for this is that this is an integral with respect to tau, and e to the minus as is just a constant with respect to tau. And so you can take the multiplication of e to the minus as inside of the integral, and I combined it with the exponential that was already there, so I got e to the minus s, and then multiplied by tau plus a. Okay, now I'm going to do a change of variables to clean up that exponential. I'm going to take that tau plus a, and I'm going to define it to be the new variable, just t. If I plug this in, I'm going to get a lot of changes. Well, in the limit of integration, if originally tau was 0, then the new t is going to start at a, so that's why it's an a at the bottom of the limit of integration. The exponential is simplified to e to the minus st now. The function of tau turns into a function of t minus a, and then the d tau is just equal to dt, so I can make that shift. Okay, so let me just focus just on that integral. What I have here is close to a normal Laplace transform formula, except it doesn't start at 0, it starts at a, and that's a bit problematic to me. However, I can actually convert this back to being an integral that starts from 0 up to infinity by the use of the step function. What I do here is I multiply by the step function u of t minus a. But the effect of that is that I can replace the lower limit of integration, the a, with just being 0. And the reason is because what the step function does is beyond a, it's just the original function. So it doesn't change anything in the a to infinity portion. But in the 0 to a portion, the step function is just all 0 there. So it doesn't matter whether I write the limit from 0 to infinity or the limit from a to infinity, because either way, the step function is just going to zero it out. The advantage, however, of writing it this way, where it goes from 0 to infinity, is this is exactly the Laplace transform. It's the Laplace transform of the u of t minus a times f of t minus a. So putting everything together, I have seen that indeed this particular Laplace transform is just e to the minus as times the Laplace transform of the little f of t, this capital F of s. All right, so let's see an example of this. I want to begin with some piecewise defined function. This function f of t is just t when I'm in the interval 0 up to a, and then it's 0 everywhere else. So pictorially, well, what does this look like? So it looks like the line f of t equal to t, but it only looks like the line f of t equal to t in the domain close bracket 0 to round bracket a. Outside of that, it's just the function 0. Now this piecewise defined function f is not written in terms of the step function. So I can't use my big formula just yet. So what I want to try to do is say, well, okay, this is some piecewise defined thing. Can I write this as some combinations of things that look like that, things that are related to the step function? If so, I should be able to take the Laplace transform. Indeed, if I try to write this as something to do with step functions, I'm going to conjecture the following. It's actually got two terms. The first term, the u of t, it deals with, well, sort of the stuff that's happening around t equal to 0. Namely, because the step function u of t is 0 to the left, which is the exact same thing as our f of t, then we match that behavior. And then when t is greater than 0, u of t is just 1, and so this looks like f of t. It just looks like this linear portion. But I can't just have the u of t times t, because after the value of a, my function needs to go back down to 0 again. So notice what I do. I subtract off a step function times t. The step function is the step function u of t minus a, which means that that step function only kicks in and starts being non-zero when t is greater than a. And then I'm multiplying it by t, and the reason here is that I get a t from the first term, and then if I subtract the t from the second term, it's going to go down to 0, and I know I want it to be 0 when t is greater than a. So what I've done is taken this function and written this as, in effect, a difference of two different step functions, and I believe it exactly matches. So if you try testing any value which is either less than 0, or between 0 and a, or greater than a, it gives you exactly what it's supposed to in its piecewise definition. Okay, well, now that I have this, I can apply the Laplace transform to it. That is, if I take the Laplace transform of f of t, which is the Laplace transform of this difference of two step functions multiplied by t, then we can use our big formula here to actually compute it. First, I'll note that Laplace transforms are linear, so the Laplace transform of this difference can just be rewritten here as the difference of two different Laplace transforms. The first Laplace transform is fine, u of t times f of t, because they both have the same argument, just t. I'll be able to use this formula with a equal to 0. But the second Laplace transform is not fine, because the step function has an argument t minus a, but the thing it is multiplied to, just t, is not a t minus a. So I need to trick this. I need to manipulate this somehow so that it is of the form where I can apply this particular formula. So what about the following? I'm going to do this trick where I add an a and subtract an a. That is, what I'm doing is I'm taking the t and replacing it with t minus a plus a, so I'm allowed to do that. But then this has an advantage. I can now split up this sum as two different things. There'll be a t minus a times the step function, and an a times the step function. That is, I'm going to get precisely this expression. So now there's actually three different terms that I'm taking the Laplace transform of. But the point is, all three of them I can apply the formula to, and I'm just going to get this. Indeed, for the first term, actually having u of t doesn't do anything at all. It just, actually just having a u of t there doesn't do anything at all, because the Laplace transform is only defined from 0 to infinity, and u of t is just 1 from 0 to infinity. It's just saying what is the Laplace transform of t? And the Laplace transform of a polynomial t to the n in general is n factorial over s to the n plus 1. So the Laplace transform of t is just 1 over s to the 1 plus 1, or s squared. Okay, for the second term now, well, it looks exactly like our formula demands. It's a step function and an f, both evaluated at t minus a. And so you get the exponential out the front, e to the minus as. And then it's just a question, well, what's the Laplace transform of t, which again is 1 over s squared. So hence the second term is this negative exponential divided by this s squared. As for the subtraction of the third term, this is a constant multiplied by the step function. And so the step function's contribution in the Laplace transform is the e to the minus as before. And then the contribution of a constant a is just, well, a over s. And so I have this final result. So here's the point. If you have some discontinuous function, perhaps a function that's defined in a piecewise way, then if you can write it as some combinations of functions multiplied by step functions, and perhaps you have to do some algebraic trickery as we just did so that the step function u and the function f both have the same argument t minus a. But nevertheless, if you can do that algebra, then the Laplace transform becomes straightforward. So in the next couple videos, first we're going to see a full example where we go start with the differential equation, for example, a mass on a spring, with some sort of discontinuous forcing and get all the way to a final answer. That's the next video. And then after that, we want to use the same kind of trickery to deal with periodic functions. So functions that do the same thing over and over and over and over again. This is a type of piecewise defined function. And indeed, as you might expect, Laplace transform is going to deal with those with surprising grace and computational power.